Hello and welcome. My name is Bo Corkins, and this is a video for the problem solving lecture for Math 1000. So, this is a general overview of everything we're going to look at throughout this entire class. And it all comes down to George Pola's four-step procedure. And this is really for anything, not just for math. Right? Understand the problem, devise a plan, carry out the plan to solve the problem, and then look back, review, check your answer. That's really an approach to everything. So, in math specifically, we have a couple of particular techniques, right? Draw a picture, make a list, guess and check, or I have PEMDAS, right? Parenthesis, exponent, multiplication, division, addition, subtraction, aka the algebra approach. And then solve an easier problem, look for a pattern. So let's look at some examples to practice, all right, these several approaches. Jenny's model train is set up on a circular track. There are 6 telephone poles evenly spaced around the track. It takes the engine of her train 10 seconds to go from the first to the third pole. How long does it take for the entire track to go, for the engine to go the entire distance around the track? Right? So we have 6 poles. Right? So first pole to the third pole. Right? So we have the track that basically looks like this. And from the first pole to the third pole, it takes 10 seconds. Well, then we should be able to do this math. Third pole to the fifth pole would be another 10 seconds. And then the fifth pole to the first pole would be another 10 seconds. Hence, it takes 30 seconds total, all right, to go all the way around the track. So that's a really good example of how a picture, all right, a picture is helpful. A rectangle has an area of 120 square centimeters. Its length and width are whole numbers. What are possibilities for the length and width? Which possibility gives the smallest perimeter? This is a really good one that represents the idea of a systematic list, right? So we have lengths and widths, and then we're actually looking for areas and perimeters. So, right, the length, centimeters, the width is in centimeters, area is centimeters squared, and perimeter, which is again distance around the shape, is one-dimensional units, centimeters as well. So just doing this, right? We know that they all make 120 square centimeters. So just to refresh on our area, right, of a rectangle, the area is length times the width. Well, that means let's start with the easiest one. A length of 1 and a width of 120. 1 times 120 makes 120. And then perimeter. It's 2 lengths plus 2 widths. Right? So 2 times 1 plus 2 times 120 makes 242. And then we can just, right, we're looking at what are the possibilities. So we can just move down the list. 2 and 60. Still 120. And 3. and 40. And we could check this. Let's see, 5 works, 6 works, right? Let's skip ahead and let's look at 8. 8 times 15, still 120. And then let's look at 10 and 12. Now notice, I know this is pretty much the last one because the numbers are almost right next to each other, right? And if they are integers, right? It says they are whole numbers, which means that I know that's the last option. And I know that this is the smallest combination, right? Because we skipped 5 and we skipped 6, just because we were running out of space there. All right. But I was like, I can see the list and I know I can see that these numbers were decreasing, all right, for the perimeter, which means I know that basically the number at the bottom was going to be the smallest one. And that's one of the big advantages of doing systematic lists. All right. Dan has twice as much money in nickels as he does in quarters. He has 33 coins in all nickels and quarters. How much money does he have? Again, I think another opportunity for lists. So, all right, Dan has twice as much money in nickels as he does in quarters. So, right, a quarter is 25 cents. So, if I have 1 quarter, in order to have twice as much money, that means I actually need 50 cents in nickels. That would be 10 nickels. And then I can identify what's the total amount here. That is 75. Actually, let's do this one in dollars. So, all right, that's $0.75. And then, all right, we're looking for 33. So notice I can already see a pattern. 2, and that would be 20. And that makes this $1.50. And then 30 and 3. And this is 2.25. And that, all right, is 33 coins totaling $2.25. So again, just identifying patterns. That's all that is. Speaking of pattern recognition, I want to follow the instructions here and see if we can identify the trick and then make a generalized statement for it. So choose a natural number, that is the counting numbers. All right, so let's pick let's pick 7. Wait, hold on. 7. Hold on. What number do I not have here? Let's pick 5. All right, so I'm going to pick 5. Now, this works with any number. I was just trying to pick a number that's not here. So I picked 5. Then I'm going to add 4 to that number. All right, then I'm going to multiply that number by 3. Then I'm subtracting 7 from that number. Lastly, decrease the result, all right, of 4, so that was my 20, by triple the original number. The original number, all right, was 5. Triple that is 3 times 5, and that's 20 minus 15, which makes 5. Okay, now you can test that with your own number as well. Now let's see if we can use algebra to identify, all right, the pattern. So that means let our number be n. Okay, n for any number. Now let's follow the sequence again. Add 4 to the number, n plus 4. Multiply the sum you just found by 3. That means 3 times n plus 4. All right, doing a little bit of algebra. And, all right, when you have 3 times, right, parentheses, if you recall, this is called distribute. I call this rainbow. You rainbow that 3 in to multiply it across both values within the parenthesis. That becomes 3n plus 12. Okay, subtract 7. So I had 3n plus 12 minus 7 gets me 3n plus 5. And lastly, decrease the result of 4 by triple the original number. So that's 3n plus 5 minus 3 times the original number, which was n, which is 3 times n. Notice 3n plus 5 minus 3n, which equals 5. Okay, so coincidentally, all right, our first number started with 5, but the idea is that regardless of what number you start with, you always, all right, will end up with 5. And that's the pattern. So that's what algebra can do for us. It can identify a generalized pattern, all right, instead of guess and check. And that's why I really like algebra over guess and check. Another example. One person earns $48,000 a year, another earns $37.50 per month. Who makes more money in a year and how much more? So person one. And this one is more, I just want to identify notation. Notice I wrote $48,000 slash year, right? Per year. It's important to get notation lined up because this one, right? This is 37.50, right? Per month. And notice the division notation. In order to get this on the same units, we do what is known as dimensional analysis. There are 12 months in 1 year. Our units will cancel, and now notice what our units are. Dollars per year. Okay, so dollars in the numerator, years in the denominator. And all you have to do with the calculation is simply just multiply, all right, by 12. This then becomes $45,000 per year. Now it's super easy to see, all right, which that person one makes more money, okay, but it's also very, very important that you understand, all right, this notation. So person one makes $3,000 more per year. But, all right, that unit for dimensional analysis is definitely what I wanted to emphasize. The local historical society wants to preserve two buildings. The total age of the buildings is 321 years. If building one is twice as old as the other, what are the ages of the two buildings? Again, I can do this with guess and check, but let's emphasize our algebra. So we have our units, right? And our favorite variables, X and Y. X, I'm going to call age of building one. Y, age of building two. So total age, right? Total. That means X plus Y equals 321 years. Now notice the other one. I'm just going to read this out like a sentence. If one building, let's call that X, is means equal, twice as old, 2 times, right? Twice as old as the other, 2y. Now I have two equations, all right? And even at this point, you can do guess and check, but let's continue this with algebra. All right, specifically, this is substitution. That is, I'm going to take this equation and put it into the other. So X plus Y equals 321. That becomes 2Y plus Y equals 321. And then I can solve that down. 2Y plus Y is 3Y equals 321. And then divide both sides by 3. Y equals 107. I can then take that value and solve it for X. X equaled 2Y, which becomes 2 times 107. 2 times 107 is 214. And then it's always good habit if it started in a sentence to end in a sentence. So I'm going to say the ages of the two buildings were 107 years old and 214 years old. Now, at minimum, if you solve this, make sure you at least put your units, all right, on your values, but it's always good to have a sentence, all right? If you start in a sentence, end in a sentence, all right? This is problem solving. This class is all about application. Basically, we don't write too many numbers without units on them. All right, let's look at one more example. Carlos has $9,000 in two mutual funds. One fund pays 11% interest and the other fund pays 8%. If his income from the two funds last year was $936, how much did he invest in each fund? So once again, so I'm going to say X equals amount in fund one. Y is amount in fund two. So the two funds together, right, are $9,000. Once again, that is X plus Y equals $9,000. It's very, very common that we have two equations and they total a particular value. This actually, first equation tends to be the one people struggle the most with. Because the second equation, you have lots of other numbers, right? One fund is 11%. Now remember, with percentages, you have to turn them to decimals. 11% interest times, all right, the amount in fund one plus 8% interest In Fund 2, totals the total interest, which was $936. Most people actually make this second equation much easier than the first equation, which is why I'm all about, all right, set up, all right, label your info. Once you're there, once again, now it's just a matter of algebra. Let's do substitution. In order to do that, I'm going to bring the x over. So I'm going to call this y equals 9,000 minus x. Then I'm going to plug this guy into the equation here. And notice the whole point of substitution, now this equation only has one variable. Now we get to rainbow. That's our big step. And then combine like terms. So 0.11x minus 0.08x, 0.03x plus 720 equals 936. And then all those years of algebra, this is two-step algebra, minus 720 from both sides. Gives 216 divided by 0.03. Gives us 7,200. And then again, this is dollars. Y equals 9,000 minus X. We can put that guy in. Which gives us $1,800, which again, as a sentence, so the two funds had $7,200 and $1,800 in them. Again, nice to end with a sentence. All right. I like that as a nice finishing touch, but absolutely those values, all right, are the absolute part that we need to make sure that we have. All right. That is everything. That was a wonderful lecture. More to come. Have a wonderful day.